ahead and continue our discussion of the reactions of alkenes. We're going to move on to a reaction that looks very similar to what we just saw in the last section here. So our last discussion looked at the reaction of an alkene plus just a halogen, right? You remember that? We formed the halonium ion and three-membered ring, it opened up anti. Except here we're going to add either water or ROH, which is an alcohol. So notice that these things are still going to be anti to each other. So the mechanism is going to look very similar to what we saw before. So notice down here it says water is the nucleophile. So it could also be the alcohol too. So water or alcohol could be used for this. Okay, so let's look down here at the mechanism. So don't forget that we're still reacting in such a way that we want to interact with these p orbitals. So we'll come up and do this first. So the first part of this reaction is like what we saw before, except we're adding water here too. So this is also aqueous, right? So get some water in there. And then we'll do the bottom one here too. So the bottom has your bromine and your water. So remember we have our delta plus and delta minus from the bromines bumping into each other. So we're going to come over here and pi bond comes up to bromine. We're going to kick off bromide. And then a lone pair is going to come over and grab a hold of one of these carbons. Same flow down below. I'm not going to put those arrows in though, just think it's going to make it messy. Now what we're given here is our intermediate, is our carbon-carbon. Same deal, you got your methyl there and your H, so those aren't changing their positions at all. And then you got your bromine. So bromine over there. And I'm trying to make it lean over just a little bit so that we can show that the bigger delta plus is at that carbon. Right, it's still a delta plus here, but the bigger one over at the carbon that's more substituted. Now as we approach from the bottom, the same idea, you got your carbons here. So now we're going to have a bond over here to bromine. And make sure we put in our plus charge there. Got your methyl, H, oops, got two wedges, H and H, there. So the only thing that differs in this second reaction here, halohydrin formation, is that we are going to have a lot of water present or a lot of alcohol. So once this bromonium ion forms, what we're going to do is we're going to have water attack. So put your water in there. And it's still going to attack the same place where the bromide would attack, right? So at the carbon that has a bigger delta plus, except now it's going to look like an SN1 reaction. So attack, lose an H. So really this reaction, even though it's new, is just the combination of two older reactions essentially. So we're coming around here. Remember here, just to point out, here you have a 3-member ring. So that always means this is going to open up anti. Don't forget that. All right, so we're going to end up with our oxygen connected to our carbon, and our bromide up here, our bromine atom. Now, the oxygen is going to have two H's and a plus charge. So they're anti to each other, right? And then let's look below and see what would happen down here. So let's come around and we're going to through this and kick that off just like so. So now it's going to be oxygen up, carbon, carbon, bromine down. And then we'll put in those H's here. So right, as you guys catch up writing that down, I just want to reiterate that we see here that anti-addition has occurred. Now, just like we saw in the last couple reactions, we just have to put in all the other jewelry, so to speak. So put in your H's and your methyls, your ethyls, and there you go. Okay, last step, deprotonation. So we're going to come through here. We're going to add water. And we're going to do a deprotonation, and that's it. So again, hopefully not too bad of a reaction. So we come around just like this. All right, we'll get the same structure, missing an H. All right, we got it in there. And then same idea down below. So just grab one of those H's. And there's where your anti. And voila, you got your H's in there. So these two products right now, these two things, what's the relationship between them? Well, if you said that they're enantiomers, good job, you're correct. All right, so then let's look at an example here down below, how we might see this, because often we don't draw the reactant like this because it's time consuming to do this. This is done really to demonstrate the anti kind of arrangement between the two groups that were added. So let me come over here and pull this up a little bit more. And let's look at this guy a little bit. So we've got some templates to fill in a second, but let's take a look. So this compound here with bromine. So I'm going to kind of do some side work over here. So we're going to add bromine to this. So, well, one thing we know is that we're going to get a 3-membered ring there, right? So we're going to have something like this occur, right? And then a lone pair for get it in, coming over, whoops, and coming over here to one of our carbon atoms. So what that will give us here is, if we're looking at it like this, is these 3 carbons. Now we're going to have a ring here, so bromine will be there. Now that's not going to be in plane, it'll either be coming out or going away, because this carbon and this carbon are sp2 hybridized, and they have p orbitals that are kind of in the z-axis. They're kind of pointing in and out of the plane essentially here, right? Kind of like that, if you can imagine them coming out like that. So for this, it doesn't matter. I'm just going to pick one arrangement. I'm going to put it out like this. So you got your bromo group here and there. Okay. All right, so, and then plus charge. So then if we just look at that one approach, so of course we're going to get the other one too, right? The dash version of this too. So now let's just look at one though. Water's going to come in. Where does water attack? Well, it attacks here. One with the bigger delta plus, because that side's more substituted. So it's going to run here and it's going to react right there. Now this bond is going to come over here to the bromine. Now there's no reason that bond's going to change its relative position. So it's going to stay out on a on a wedge, basically, still, right? So what I want to show is that. Let's zoom out just a little bit. And let's take a look at our structure here. So that little guy in blue is really this guy here. Right, so we're going to come over and kind of join in here. Okay, so if my bromo is here, right, and I know that they're anti to each other, then my oxygen, right, must be right here. And let me make this a little smaller. OH is there. Now this is water, and then here let's have the loss of an H plus, right? Because once water attacks, you get the OH2 plus thingy on there, and then you lose a hydrogen, right? That's the end result. So you get an OH and a Br. And then this is an H, an H, and an H. So that's our bromo on a wedge. So if we attack and did this, right, if we came the other direction and did like this guy, right, then our bromo group would be on a dash. Now if we know that we're anti, then that means that the OH must be here, and then voila, everything else is an H. It's unnecessary to show that here because this is achiral. So probably what we would do for our final product is write an H, an OH, and just throw a Br on there because it's not chiral, right? So there's your bromo group there. And now we had our OH here on the wedge, so we'll keep it on the wedge. And that would be your two products. And again, these are enantiomers of each other, okay? So the next reaction I want to take a look at is epoxidation. So epoxidation uses this big crazy compound called MCPBA. So MCPBA is the following molecule. So I'll give you some history of it. So there's benzene. That's benzoic acid. And so what MCP stands for is metachloroperoxy. And the peroxy is when we have an OOR group. Or it could be an OOH group. So if we take that and we put a chloro group on it, and we'll learn about what the meta means. So let's leave it like this for right now. So meta is here. It's a chloro group. And an OH down there makes it a peroxy acid. So this is MCPBA, also known as metachloroperoxy benzoic acid. That's got a big scary name. All right, and just kind of cross that thing out. Little dot there. So here's the reaction. An alkene, peroxy acid, you get this thing called an epoxide. So we want to know what epoxides are. Epoxides are going to show up again in chapter 14, and they can open up under two conditions, under acidic or basic conditions. And then you get a carboxylic acid, and this is often a PPT, right, a precipitate. All right, so here's the good news for you. That's the reaction that you need to know. The mechanism is not a reaction that I'm going to require you guys to learn, but I have it written down here for you guys. It's called the butterfly mechanism, primarily because the intermediate, looking at it the right way, kind of looks like a butterfly, I guess. So peroxy acid has an interesting electron flow if you look down here below. So coming up here to our oxygen, moves to this position, that guy comes down and grabs an H, and then we swing down here to our carbon. So that's how we're going to show the transfer of electrons. In the end, we end up with the epoxide and the carboxylic acid. Okay. these rings are going to be able to open up in the presence of an acid or a base via different mechanisms. So we'll see in our next lecture how it opens up in an acid, and then later this semester we're going to see how they open up in a base. That is chapter 14.